Okay. All right, good. We're recording. Great, awesome. By the way, I was close to the Niner score, but our defense could not show up. I was like, look, I'm gonna be right. Perfect. 24-17. And it's frustrating. Anyway, I really thought I was gonna be spot on. It's just our defense couldn't show up and our offense couldn't put the game away. All right, sorry, I digress. Okay. It was 27-24, but it was 24-17 with like 4 minutes left in the game. So all right. Y equals cotangent x. Okay, so we know how the graph looks, right? Domains from 0 to pi. So those are the asymptotes, 0 and pi. The range, we know that. So you expect domain range to switch, right? And I'm going to close some stuff here because this is getting a little annoying with the sluggishness of the computer. Okay, thank you. Jeez, that took a while. That just make it worse. Hold on. Oh my goodness. All right. Okay. So you're gonna switch it, right? Negative infinity to infinity. And 0 pi. So everything switches. So your asymptotes will switch too. You have an asymptote y equals pi. And asymptote y equals 0. Now we had a tech issue with this last class, I think on Wednesday or Thursday, but the Wi-Fi went out. Okay. So it's just AP is just bad luck. I don't know what's going on. All right. Also, you're gonna have some other points switch too, right? If I do a table for the parent function, okay, that's a little better. That's sluggish. That's good. Pi over 2 comma 0. Bless you. Pi over 4 comma 1. And 3 pi over 4 comma negative 1, right? They all switch. So you have a point at 0 comma pi over 2. So by the way, this is at pi over 2, right? And then you have a point at 1 and negative 1. So 1 comma pi over 4. And then 1 comma 3 pi over 4. So remember, everything switches. So 0 pi over 2, 1 pi over 4, negative 1. That's a crazy looking 3 pi over 4. And remember, it has to be a reflection about y equals x. When you do when you flip the original to the inverse graph. Does that make sense? How I got that? Yeah, because if I did this, right? And graph y equals x, they're reflections of each other, but y equals x. I know I kind of did that very hastily, but you get the idea. Okay. So the unique angle y in the interval from 0 to pi is denoted by the following: inverse cotan of x, or we do arccotan, my apologies, arccotan of x. Okay, so we're okay with that? Remember, the output's the angle. The input is a combination of x over y, right? Because remember, tangent is y over x in a circle, cotangent is x over y. So these are all like ratios of x and y on a circle, which makes sense because at 0, sorry, at pi over 2 radians, the ratio of x over y is 0, right? We know that. Okay. Domain range, I already wrote it. We don't have to write it again. So let's just move on to some other stuff here. So the default range is from 0 to pi. Okay, that's what's happening there. So with that said, I could do 75 now. Now I feel comfortable talking about 75. So if your angles, okay, if that input is negative, right? What quadrant am I in now? Q1 or Q2? Q2, right? So yeah, because inverse tangent is Q1, Q4. This is Q2. So do a quick sketch. Say good.
In the homework, the axis was greater than 0. So
right, but you have negative 3 over x. You do negative 3 over a positive. If you put the negative next to the numerator and make x positive in the denominator, you have a negative over a positive, still a negative overall. Because when I draw the triangles, remember, it's inverse cotan, right? So this is going to be adjacent or opposite. Does that make sense how I drew that? Because think about it. What's going to be the inverse tan? That'd be x over -3. So opposite over adjacent could be inverse tan, but if you do inverse cotan, it's adjacent to a over o. Adjacent or opposite. So it's a lot of like backwards type of thinking you have to do here. So that's why I do a over o, -3 over x. Now how do I get that back? Yeah, and by the way, this should be negative, it's going to the left, and this should be positive, it's going up, and x is positive, you told that. So now I feel good about it. Everything's confirmed. If I do Pythag, I should get √9 plus x squared. Is that correct? Yeah, or x squared plus 9, whatever you want to call it. Now I want the sign of it, so just opposite over adjacent. Sorry, opposite over hypotenuse. Now you can easily get these things backwards. You get this here, and everything's positive because you told x is greater than 0. That's how you do that problem. So hopefully that makes sense. Whoever's asking about 75. So hopefully you're okay with that now. All right. Okay. That's better. Okay. I feel so much better now. All right. This is probably good. I don't want to take too long with this because I'd really want to get back to I really want to finish off these notes. But let's do maybe just D and E, and we'll come back to ABC if we have time. Let's look at D and E. Okay, what quadrant am I in for this one here for part D? Remember, you're dealing with inverse sine. Which one is that going to be? Q4, very good. -5, 13. Always make the hypotenuse positive. That's 12. Tangent's easy. -5/12. Super easy, right? Not that hard. What's cosine of pi, guys? -1, very good. That's the same thing saying inverse tan of -1. Same thing, flip -1, still -1. Where does that happen? Actually, I should not do that. I should not do that. I just realized, what's my default range of inverse cotan? Yeah, so I should not be flipping that. I could do, okay, so that flipping thing makes sense for inverse cosecant and inverse secant, because inverse cosecant and inverse secant have the same ranges as inverse sine, inverse cosine. But yeah, I can't. I have to use my default range from 0 to pi, non-inclusive because I have asymptotes there. So yeah, so what's going to be 3 pi over 4? Yeah.
Flip any problems?
Well, you could. Let me think about this. You could flip it in the sense if you want to understand how the tangent will look, but you can't put it in the fourth quadrant. You have to put it in the second quadrant. Yeah, you have to put it in the second quadrant. Yeah, so it's 3 pi over 4. That's a sneaky one. With that said, let's look at example 5. Part 5B is going to be a little tricky. Okay, so remember, this is your angle. Right? So tangent theta equals x over 1. X is positive. We're in Q1, right? We're going to be Q1. X and 1. Pythagit, what do you get? 1 plus x squared. What's the sign? X over, and you do not have to rationalize, by the way. Don't do the work that I'm not going to give you credit for. It's a waste of time. Just leave it like that. I'll even say so. Actually, the entire test, I do not want you guys to rationalize it. If you want, go ahead, but leave things unrationalized. I won't give you any extra points for it. Okay. Now this one. X is negative, and you have this here. This is theta again. So cotangent theta equals 2x. We'll say 2x over 1. So remember, this is your adjacent, and that's your opposite. So I had to do in Q2. This is Q2, guys, not Q4. X is negative. So I feel good writing this then. Because that will make that a negative side. Because you're on the negative x-axis, and that's 1.
You say 2x or negative 2x?
No, you say 2x is inherently negative. Don't say negative 2x, it'll be back to being positive. Don't do that. Yeah, don't do that. Because x is already, this is inherently negative because you told so. So you have to do not put a negative front, because then it's just incorrect. Do not put a negative front, guys.
Does that mean that?
Either way, it's gonna have you're just gonna swear and you'll get rid of it.
No, it won't matter for the hypotenuse, but it will matter for the final answer.
And
So when you do that, you're right, Thomas. For the hypotenuse, it won't matter. It'll be 4x squared plus 1 rooted, right? And if I want the cosine of my angle, that's adjacent over hypotenuse is 2x over root. But see, if you put a negative out in front, your answer would be incorrect. Because now that's not going to be a positive answer. But remember, cosine is negative in the second quadrant. And you're told right from the get-go that x is negative. So you got to leave it like this. So, yeah. So I'm glad we're having this discussion because I know I didn't talk about inverse cotan. Now I have, feel better about that. And it makes sense when you look at the graph of cotangent. So that, the default range from 0 to pi. Okay, we're okay with that? All right, good. Okay, now we can actually, now I can see the light at the end of the tunnel. All right. So part 7, the last part of the notes. And I'm glad we're not doing homework quiz either, because I just don't think we have time for that. And we got to start doing review. And finish the notes. So you're just solving equations. That's all we're doing here. It's really just unit circle stuff. That's what's happening. Like we know what's happening here, right? What's my default range for inverse sine? We've talked about this a few times already. Thank you, Thomas. Yeah. Inclusive.
Why does inclusive matter?
Because you want the entire output. So that the entire output for sine is from -1 to 1. When you think about the inverse, sorry, when you think about the sine graph, y equals sine theta. If you want the complete range from -1 to 1 inclusive, right? So when you do inverse, you have to make sure that you're using that as your input.
But it's not going to be a triangle.
Fine, it won't be. That's okay.
No.
Yeah, if it collapses.
Oh, right.
That's what we call quadrangles. These are angles that happen at the quadrant boundaries at like x-axis, positive negative x-axis, positive negative y-axis. That's all.
Oh, and the other ones are non-inclusive.
Of course. Correct. Right. So this only happens, guys, at pi over 3 or 60 degrees. Now, let's do a little partition here. This is different. Because what this is telling me is that I want all possibilities. That's what that's telling me. I want all possibilities. Yeah, correct. Because if you think about the sine graph's this, right? And where's sine gonna be root 3 over 2? Infinite possibilities. So I want actually all the possibilities for this. So what would be equal? Well, definitely it happens at pi over 3. Definitely happens at 2 pi over 3. Definitely happens at 7 pi over 3. What's positive? Because I've gone around the circle once. 7 pi over 3, 2 pi plus pi over 3. Right? And then 2 pi plus 2 pi over 3. Would happen at -4 pi over 3. Yeah. Yeah, exactly. So I don't, I'm gonna stop writing because I can't. So right. So here's the deal. This is how you write it. You're gonna write like this. Where n is any integer.
Wait, that says 2 pi over 3 plus 2 pi.
2 pi over 3 plus 2 pi n.
Oh. Wait, why?
Cause that means you go around.
The 2 pi over sine 2 pi over 3 is root 3 over 2. So sine
But
pi over
not-
3.
Oh, yeah, you do both.
Right. So here's the deal. When you put this 2 pi n business, that's called a general solution. Did you guys talk about general solutions in Mr. Band's class? Nope. Okay. I gotta have a conversation. I gotta take him out to lunch to figure out what he's telling you guys. No. I know he's using CPM. I don't know. Well, it's good for regular.
Yeah.
It's a little tough for algebra honors. Well, honestly, when I taught algebra two, those pre-pandemic, when we had more instruction time and more contact time, I did do this, but that was like, gosh, 8 years ago. So, anyway, that's called a general solution because generally is what we expect to happen, right? Because we can go around a gazillion times, backwards, forwards, whatever, and still land in the same place. So you have to give that as a general solution. That's what's meant by general solutions here. Okay, question. Go ahead, Thomas. Your question.
And like, if you're asked this question, you just know, how'd you know it's asking you all possibilities?
I would say find the general solution.
Oops.
I would explicitly say, like in the instruction for example 1, that's a no. Yep. If I give you an inverse sine as a non-calculator question, so the other thing about our test, well, we haven't really needed the calculator, to be honest with you, for this unit. So I'm debating as to whether I'm going to allow calculators for part of it. Definitely, this would be some parts without a calculator, 100%. I still have to write the test, so I got to do that later tonight because I got to get that done. But there will be some part where you have to do without a calculator, like this one right here, right? That has to be done without a calculator because you got to know your unit circle. So if I give you an inverse trig function, yeah, just give me the default range. But if I say provide general solutions, then I want all possibilities. David, go.
I don't understand what's different between A equals arc sine of.
Between these two?
Yeah.
Okay. So this one, remember, we want to guarantee that this is a function. You want just one output. Okay. Actually, I should have said this earlier. You want just one output. Because you want to guarantee that inverse is a function. That's why. Here, multiple outputs are okay.
Like you wouldn't just.
Oh, it's because there's a default range for.
Correct.
Arc sine. And
Correct. Right. Exactly. But in order to make the case that an inverse trig function is a function, or an inverse relationship is a function, you have to have just one output.
Yeah.
Whereas here, I know there are multiple outputs for sine. Give me all the inputs that provide that. That's what I'm asking for. I'm being just super intentional about it. Okay, example 1. Let's look at this one here. So all you're doing is this. Cos x equals root 3 over 2. Now notice I asked 2 things. The general solution and the first 3 positive solutions. Not that hard. First of all, where's cosine going to be root 3 over 2? What quadrant can I start with? Q1, and that's going to be at pi over 6. Where else does it happen, guys? Well, no. Let's go counterclockwise. No, it's negative 11 pi over 6. Okay, where else does it happen? 13 pi over 6. Are those my first 3 positive answers? They are. And my general solution is going to be pi over 6 plus 2 pi n, 11 pi over 6. And let me be kind of clear about general solutions, just so you guys know my expectations. Because maybe I don't have made this clear. For general solutions, find all angles that make the equation true from okay. So for general solutions, this is what you do. You find all angles that make the equation true from 0 to 2 pi, and 0 inclusive, 2 pi non-inclusive, because 2 pi is the same thing as 0, right? Otherwise, then you're kind of beating yourself. Then add 2 times 2 times 5 times 10 afterwards. That's what I did. Pi over 6, 1 pi over 6 make that equation true, right? And add 2 pi. So now 13 pi over 6 is covered, or 23 pi over 6, and so forth. So that's what's happening. So that's example 1. Questions on that one? Okay, example 2 gets a little crazy. Yeah, for example 2, can I erase? Nope, I'll wait. And while I'm at it, let me pass out the review packets. Some people. Like. I'll wait so I can work. I'm gonna take one through here. I'll get these tables. And then pass. Yeah, go. All right, let's keep moving, guys. Okay, so example 2.
Yeah.
Okay, can I clear now? We're good? All right, let's clear. All right. Example 2. Now this one's kind of crazy. Guys, quiet please. Because you see a 3x here. This is a little crazy. You'll see why in a moment. So 2 sine 3x equals negative root 2. Sine 3x is negative root 2 over 2. Okay, this is a little crazy. I told you it's going to be a little crazy. So not x, but 3x. Where's sine negative root 2 over 2, guys? Go, Elsa. 7 pi over 4 and 5 pi over 4. Good. Yep. Okay. So that's going to be 5 pi over 12. And that's going to be 7 pi over 12. But here's the deal. 7 pi over 12 is barely in the second quadrant, right? There's going to be more. What? Think about it. 3x. You're going to have triple the usual solutions.
What?
Yeah. Here. Your mind's gonna be blown. Check it out. Yeah, what am I talking? I don't know what I'm talking anymore. No, I'm not gonna make a stop. I'm gonna keep going. I'm just making random crap with you guys. All right, well, back up. Back up a little bit, guys. All right. So here's the deal. I need to find all the possibilities within the first rotation of the unit circle, right? Because whenever you say 2 pi n is a general solution, yes, the general solution here. I have to find all possibilities within the first rotation. Think about it. You got 3x. That period right now is only 2 pi over 3. So I gotta do this 3 more times. I gotta do 2 more times. I need 6 solutions within the first rotation. Because I had 2 in the first rotation, but 3x. So yes, it's kind of crazy a little bit. Oh, so guys, how did I get 13 pi over 4, 15 pi over 4? I added 2 pi to 5 pi over 4, and I had 2 pi to 7 pi over 4.
Why is that not included to 5 pi over 12 plus 2 pi?
No, I have that. Okay. Okay, let me actually, you know what? Let me back up a little bit because I think I'm freaking you guys out a little bit with this stuff. Actually, you know what? Let me back up a little bit. Okay. You know what? Let's do this. Let's back up here, guys. Okay. We have this, right? You guys okay with this so far? We're okay with this? Agree? Okay. Let me actually write the general solution, but I'm going to do a little twist to it. Okay. This might be better, actually, the more I think about it. Okay, here we go. All right. This might be a little better for you guys. Okay. This might be one way. Actually, I'm kind of glad I scared you guys with like there's gonna be more solutions, but this might be a better way of consolidating everything. Instead of writing 6 solutions plus 2 by n every time. If you think about it, okay, so 3x equals 5 pi. Remember, 3x is your angle. Yeah, thank you. I agree, Thomas. Yes. So 3x equals 5 pi over 4. So x is 5 pi over 12. Cool. 3x equals 7 pi over 4, because 7 pi over 4 sine of 7 pi over 4 is also negative root 2. But we solve for x, we get 7 pi over 12. But we have to realize that, remember, the period here is 2 pi over 3. It doesn't cover the full rotation in a circle. So what you do is write the general solution. Fine, 5 pi over 12, but you gotta say plus 2 pi n over 3, where n is any integer. This way, when n is 1, what happens if I have 5 pi over 12 with 2 pi over 3? 2 pi over 3, I can change it to 8 pi over 12. You'd agree with that, right? 2 pi over 3 is 8 pi over 12. Add the 5 pi over 12, you get 13 pi over 12, which I showed you was a possibility. Likewise, by 2 pi over 3 plus 7 pi over 12, that'd be 7 pi over 12 plus 8 pi over 12, 15 pi over 12. That's yet another solution that could work as well.
So how do we write those first 3 negatives?
Great question. I don't know. No, just kidding. No, I do know. I'm just messing with you guys. First of all, you have to state this, guys. Very important. Yes. That's a formality that I want you guys to state. You have to say n is any integer, right? Because there are going to be some more complex ones down the road, not this unit, but the next unit, where n might be an odd integer. It might be something else. Like you have to be kind of explicit about that. Okay, first 3 negative solutions. So what I'm going to do here is simply just use my general solution to get the negative solutions. So let's say when n is -1. So to find the first 3 negative solutions, and we'll go to Desmos just to verify this. So let's say n is -1. Then I'm going to have 5 pi over 12 minus 2 pi over 3. Also, I'm going to have 7 pi over 12 minus 2 pi over 3. And I'm going to have to do 7 pi over 12 minus 4 pi over 3. If I work all those out, I should get, I need to clip some space here. If I work all those out, 5 pi over 12 minus 2 pi over 3, that would be -3 pi over 12. Is that right? Yeah. And then this one here would be -pi over 12. And this one here would be negative, hold on, -9 pi over 12. Yeah. It's a good idea. If you don't, I won't hold it against you. Now I'm gonna graph this just so you guys can see how it looks, so we can verify this. But what I did was I had to look at my general solution and say, okay, when's the first time a negative answer happens? It actually happens for this one. Because if I take away 8 pi over 12 from this, that's -pi over 12. That's actually the first negative answer before this one, right? Or that makes sense. That's closer to 0, but negative. Then if I make that negative, okay, great. Then, but that's a little bit smaller, right? Than -pi over 12. And then I do negative, then I do 7 pi over 12 again, but do a negative 4 pi over 3. So let me show you that general solution right here. Let's go back to Desmos. What's up? That's if Google Chrome wants to open.
Do we have to like verify that? Are those always going to be the first 3 negative solutions if n is -1?
It depends on the situation.
Okay,
So
we can't just plug in.
You have to see which one happens first between the two. So Okay, Desmos. Someone's gonna have to refresh their computer today. This is silly. What the heck is going on here? There we go. Okay, well, I know this works, but I just want to prove to you guys, and now Desmos just wants to. The computer just doesn't want to act properly today. Let's give it a moment. Okay, while that's happening, hold on. Okay, maybe we'll get going. Okay, y equals, what was the equation again? 2 sine 3x plus what? Root 2? Okay, cool. All right. So you want to see where this equals 0, right? Let me clear the. Okay, so 1, 2, 3. This is why Desmos is so awesome. Because it gets the answer pretty quickly, so you can verify your work that way. Exactly. We should have Desmos. Hey, so allow on the SAT, right? We should allow on our test. I don't know how we're going to make that happen because it could, you have to use a computer and there's other issues that come with that. But see how this makes sense, right? So this is why we have to do this. So now that we've kind of done one of these, let's try another one. Let's look at the next one here. Example 3. All right. Move the 4 over and divide 2. I trust you guys can do some of the algebra steps. You can combine 2 or 3 algebra steps at once. So subtract 4, divide 2. Does that make sense how I got that? Right? Subtract 4, divide 2. Then 4x plus pi over 2. That's my angle. So this is like theta, right? That's like theta. Where's cosine negative half? Q2 and Q3, right? More specifically. Good. Excellent. Thank you, Kieran. So I do that. Fractions. You gotta be cool with your fractions. So that's gonna be don't tell me. Pi over 6. 8 pi over 12 minus 6 pi over 12. 2 pi over 12 should be pi over 6. Or 4 pi over 6 minus 3 pi over 6. Yeah, I don't know why I did 12. That's dumb. So x is pi over 24. But you gotta write plus 2 pi n over 4. You're always going to do divided by whatever the b value is to guarantee that you get all those possibilities. And in here, a pi over 6, 5 pi over 6. I mean, you should reduce the 2 pi n over 4 to pi over n over 2, but it's okay. You can leave it like that. So those are my general solutions. So I'm pretty consistent here, guys, right? And then to find the first 3 positive solutions, obviously pi over 24 and 5 pi over 24. And then, of course, pi over 24 plus 2 pi n over 4. So my first 3 positive solutions will be pi over 24, 5 pi over 24, and then pi over 24 plus pi over 2, which will be 13 pi over 24. Yeah, I think that sounds about right to me. Yep. And again, use Desmos to verify your work. It'll get us that answer. So actually, just my OCD kicking in a little bit. So let's do this really fast. 4x plus pi divided by 2. What was it?
Plus 4.
Well, let me do this plus 1. Let's move it over. Yeah, pi over 24, 5 pi over 24, 13 pi over 24. Boom, boom, boom. There you go. Okay. Let's keep moving. Say, go ahead.
We, just need to pick the first three positive solutions. Can, do those include 524 and 5?
They do, 100% they do, because they're positive, yes. But of course, with the previous problem, we had the negative answers because the general solution had positive answers. So we had to make, we had to find 3 new ones, right? Okay, find where this is undefined. Well, let's see, that would be undefined at what angle is secant undefined, guys? At the pi over 2 and 3 pi over 2. So that's going to be at pi over 3. And pi. Yeah. And this is a little bit messed up because it's 3 halves. So you guys pi over 3. Or you can write pi over 3 plus 4 pi n over 3. When you flip the 3 halves. And then here, so you always divide by whatever b is, the coefficient of x, to guarantee all the possibilities. Because your period is going to be 4/3. 4 pi over 3, sorry. So you can see why I'm doing this, because I'm trying to guarantee every cycle of this graph of secant, right? Because the period is 2 pi over b, my b is 3 halves, so my period of length of one cycle is 4 pi over 3. So that's why we're doing this, guys, because you're trying to make sure you get to every cycle of that. That's what we divide by that value. So yeah, because you're gonna drive yourself nuts if you try to find every single one from 0 to 2 pi. Just do 2 pi n divided by b. So remember, we're just doing this plus 2 pi n, the coefficient of x. 3 halves. Right. Okay. And this is a fun one. Find the third negative solution. So you have to kind of do a little counting. So in order to do that, you'd have to plug in -1 for n into both. See which one happens first. And whichever one happens first, then plug in -2 into that to get the third negative solution. So in this case, if I plug in -1 to this one, that will be negative pi, I think. If I plug in -1 to that one, that's going to be negative pi over 3. So definitely this is the first one. So if I plug in -2 into that, I get -7 pi over 3. Is that right? Wait, did I mess up the first one? Oh, I just do my math for the last one incorrect. You're right, you got it, sorry. Yeah, -5 pi over 3. You're correct. Yep. It's -5 pi over 3. Good. You guys are getting that. Good. Okay. Okay. I've decided, because I'm in all likelihood, I'm probably gonna make this a non-calc test. Oh, sorry. Okay, sorry. Let's forego example 5, because I see also time's kind of running out too. So let's forego example 5, because because that's a different skill set that I feel I need like more than 2 or 3 minutes to do, and I've given you guys a lot of information today. So let's ignore example 5. I'm not gonna put example 5 in the test. I can save that for the next unit, so not a big deal. Let's not do example 5, because that's gonna be a skill set you have to use a graphic calculator, and you have to kind of find the intersection points and all these things. I don't want to do that. I think I've kind of made myself clear how to do these other ones without a calculator using unit circle. Say, go ahead.
-5 pi over 3 for the lots.
How I got that?
Yeah.
I put -2 in for n.
Why don't you put in -2?
Because I first had -1 for each of these. I got negative pi over 3. So negative pi is the first one. Negative pi is the second one. This has to be the third one. It's just a counting thing. Okay. Last one to sneak in here. This one's no different than I'm not gonna do this in 80 seconds. I will talk about example 6 tomorrow, because I do want to ask that on the test. I'll talk about that tomorrow. I'll let you guys kind of figure that one out. Let me go check the copy machine and give you guys these other 2 tables. I'll give you guys details about the tests tomorrow. I'll talk with some of the schools you later this afternoon. It's just under, that would be open to that one. Let me get. Back to you guys.
Is it extra? What's the packet called? Where is it? It's not turning on. What did they just stand up? This?
Oh, yeah.
Yeah.
Well, the copy machine didn't do me a favor, so I only put it one, so if you guys wanna hang tight, you guys there, just give me like 3 minutes, the officers, I'll get like copies for you guys. Not yet. So the rest of you guys hang tight, I'm gonna print.